I will start from the overfitting, underfitting. I think most of you are familiar with this, hopefully. But just a little bit warm up. Can you tell me if your model overfit, is this training loss or training error actually equal to, if it's a classification, that equal to 1 minus accuracy? Whether these loss errors would be big or small? Just give me type your answer in the text box. In the case of overfitting, and you please text two answer, one answer for training, another answer for the test error, big or small. So give me 2 words. Overfitting, small, big, overfitting, small, big, small, large, all good. Yeah, Margaret and Baron has good understanding. I think most of you have good understanding on this part. So now how about underfitting? Still, give me small, large, or big. Will we get small trailing loss or big trailing loss under the scenario of underfitting? It seems opposite from before. You know, if now it's not that easy, not update from before. One little bit change. Test loss is same as before. It's also big because it's underfitting. That means it doesn't know anything. If it doesn't know anything, how it can perform on test data? So it's just randomly guess test data. But it also don't know much about training data. So it can't perform well on training data neither. So that means it also have a big error in training data. So oh yeah, so update from before is the training loss is operate from before. Before the training loss is small, now the training loss is big. But for the test loss, it will be the same, okay? Because both two cases you won't perform well on the test loss, okay? Clear? Any question for this part? Yep, I think all people is good with this. So since you are comfortable with this, now I need to give you a little bit more challenge to look at the specific algorithms that is decision tree. Maybe you will know what we will talk about today is decision tree, different a lot of trees. So we have random forest, we have a gradient boost, we have other boost, just a lot of tree. Why we need a lot of tree? Because the decision tree is an algorithm easily overfitting to training data. So that's why we want to introduce more tree to overcome this overfitting problem. I will go into detail why decision tree will lead to the overfitting problem so easily than other models, and why introducing more tree will reduce this overfitting problem. And actually, we not only introduce more tree, actually we also do something on data. Yeah, before I go into this, since I talked about the data, anyone know what random forest does for in terms of data? You know, we have training data. What random forest does for this training data to overcome the overfitting problem of decision tree? I just want to test if you have, have some detailed knowledge for this. So never mind. If you don't remember this, I will discuss later. Improve accuracy, that's a result. It will improve the test accuracy. But what operation it does to make such good results? Because you all of you should be on Tuesday's lecture, so I think let me have a test if you understand. Actually, I didn't go to lecture, but I think lecturer will talk about this. Thank you, Margaret. Yeah, bootstrap. So that's the technique we use to overcome the overfitting problem. But I think some students still maybe confused on this bootstrapping technique. So let me make it mysterious for a while. Then I will discover this in detail. So okay, so let's have a problem here. I make some data. Okay, how I make this data? I make this data just, I do some training, I do some sample size. Oh, I make too much. Okay, just make 20 test data. Okay, I don't want too much test data. So I make 5 feature in this data. I want to have a 40, size of 40 training examples and 20 test examples. So each features, these features are highly correlated. The correlation is 0.95, 95% correlation. So basically they have very similar semantics. So normally the model only needs one feature to do the prediction. So now I deliberately, generate this synthetic data. Then I use decision tree to do prediction. You see, now I have overfitting scenario, right? Because training data is big, and training accuracy is big. That means training error is small, and this is training error is large. The training error is 25%, right? This training error is 0. That means the model learn training data very well, but it can't generalize, perform such good performance on test data. So anyone have a understanding why it happens according to what I told you about how decision tree work? Maybe if you can even give me a solution how I can do something without introducing more tree do bootstrapping on data. What could I do to make make this result better? We have highly correlated features in this data set. Then we use tree. I set max depth 15. Then I fit it. I predict it. I get training accuracy. I get text accuracy. Then all fits. Any understanding why does it overfit? And even any improvements I can do? Yeah, great. Let me see what Amma said. Will train overfitting? Yes, that's will train overfitting, obviously. You're correct. And use mean sample leaves. Yeah, using mean sample leaf. That's also correct. But I want you to have understand why it happened here. Let's see. I have a highly correlated feature, right? So that means if I do the splitting, I only need to do one splitting to have the to capture the most of distinguishable semantics, right? The rest of features, if you keep do the splitting, you you mostly will go to the noise information. Why? Because most of information is are contained in each of the feature. You don't need too much feature. If you go to too much feature, then you go deeper. Actually, you will make your decision. You will make the splitting. In tree we have splitting. You will make a splitting according to the noise information rather than the the generalizable information in this 95% semantics. So just have a look. I think we are confident it will give me see better. Sure, that's because I deliberately generate data in this way. So you can see how I generate data. Sorry, I don't think you need to look at this because I use a multivariate normal distribution. The only thing you need to, if you're interested in how I generate this data, you can go to the code. But the only thing you need to know is it has each pairs of feature has 95% correlation. That's what I want. Yeah, I think this is a very interesting toy example. Hopefully you also think it's interesting. But any question for this before I go forward? Now I show you decision tree is easily to overfit, especially if you have a small number of sample size. Most importantly, you have highly correlated feature. So that means this feature have noise, then it will have it tend to overfit. So I think a theme of AMA said to increase the minimum example in leaves. Let me go back to the chat box to have a look. Oh yeah, I think say that minimum samples in the leaf. Actually, it's same. If you increase the minimum sample in the leaves, it will early splitting. Do early splitting. Why? Because it will keep three. Then it's only 40 examples. So you do one split. Maybe in one node, it only have 20 examples. So you said minimum sample in the leaf is 20. So it will stop here because it's already 20. So you can do that. Same thing. Okay, so this is one strategy to do the, to avoid overfitting, but it's only in this particular case. But generally, decision tree is, if it keeps splitting, the tree structure actually bring the depth of tree structure actually bring the overfitting to more general problems. Beyond this highly correlated data. So normally the people derive some algorithms to overcome this problem. As I said before, they build multiple trees to do the thing. So now today I will introduce random forest. That is most popular one we will use actually 5 years. I mean, before I start my PhD, I think before 2018, most of people will use random forest to do Kaggle competition. So one idea of overcoming the overfitting problem is bootstrapping, as Margaret said. Why we do bootstrapping? Because basically I want to know anyone know what the bootstrapping does for a data set. Because if you know what bootstrapping does, I think you will have a very much intuition why bootstrapping work, why we want to do bootstrapping. Random selection with replacement. Great, Margaret. So now I think you have some idea why we do bootstrapping. You mean we do random? I think I don't give you big picture so far. So let me give you big picture. You have training data X, Y, right? bootstrapping do is, okay, just randomly select example from X. I do the I give a random index and select the X this for this index. So now I do it repeat I repeat this process. Then I get maybe 30 example for training. So in this 30 example, original we have 30 example. This is original example. Now we have a bootstrap one. It's also 30 example, but it doesn't contain some example in this 30 example, right? Because it's do some random pickup, so you have some randomness, so you don't pick up some of examples in this original pool. So now you do bootstrap 2. We also have 30 example still, because the random sampling from the original pool. This 30 example also different from these two sets of 30 examples. So now I think you have intuition why it will help, because if you train one tree on this training data, train another tree on this training data, there are different training data, some noise in this training data, but not in this training data. So now for this, you have an orange tree, right? Maybe you do a prediction for test data is equal to maybe 1, but this one is not correct because you have some noise, right? The model overfit to the noise, you have some incorrect prediction. But now it may also have noise, so it has some probability it will. The y true is, let's say the y true is maybe 0. Okay, so this is binary classification. So if the y true is 0, this is 1 because of noise. This is maybe okay. The noise is accidentally removed because you do random sampling, so it's possible you remove some noise. So okay, now it's correct. Then for this, maybe the noise exists, then it's not correct. For the next, maybe the noise also exists, but but generally, I don't want to make it binary classification. I want to make it like 3-class classification. So this is 3-class classification. Why I make 3-class classification? Because it helped me to demonstrate the idea. Okay, so now this is 0, right? Now here it also have noise, but it has different noise because the random splitting is not the noise won't be completely same as the noise here, right? So because because the different noise, it could be class 2. Then we make another prediction of another tree. So this would be, if it doesn't have noise, it would be 0, right? It has noise, maybe becomes some other class. So I make another one is no noise, is 0, 0, right? So now you should understand my idea, right? Then you can see the mostly in general, the true prediction will appear much more frequent than the others. Why? Because the others depends on noise. The noise is random, right? But the generalizable knowledge is not random. The generalizable knowledge should be applied for every example. So that's why finally, if we make a vote, we will say, okay, how many 1 we have? Only 2. How many 0 we have? Oh, it's 3. How many 2 we have? Is only 1. So we will choose 3. If you keep doing this bootstrapping, maybe 1,000 times, you will find the 0 will appear much more frequently. Okay, understand my idea? Any question for this? Yeah, great. If you don't have any question, let me go to the implementation of the uh, the random forest. So actually, it's easy, right? We just do bootstrapping. You say here I do 5 times. Now I do 2,000 times. Then I get the training data and to train the the tree, right? So I train the tree feeds. Then I add this tree, right? So now I have 1, 2, 3, 4, 5. Actually, I have 2,000 tree here. Now I do the prediction. Okay, I do the prediction. Um, for for each example, I have a 2,000 prediction. So I have to average across these 2,000 prediction. Then I will get the final prediction. So I do voting here actually. So now if you look at the results, it's actually better than the let me just copy paste this to the previous overfitting design tree. So you have more intuitive. Let me go to the previous. You see, previously we have. I don't make the depth to 2. I just make it to uh 14. Actually, that is okay. So let me do something here. Okay, I do bootstrapping. I also using this random forest classifier. So what I want to make sure is, okay, let's try and make the maximum depth send, whether it will still give you better result with only the bootstrapping. Because here I get the better results. Actually, I already set the maximum depth equal to 2. So you may set, okay, it's because you make the maximum depth equal to 2 rather than the bootstrapping technique, right? So now I actually want to make all the thing exactly same, except I use bootstrapping. Let's see whether the result will be same. To be honest, I don't know because I didn't run this code before. I just, I just devised this material yesterday, so I haven't go through all the details of this material. Let's have a look. Actually, I think it will work, but I also just want to confirm this experimentally. Is it work? Why I have a 2 version. I have another version here. Prediction on training data, prediction. Oh, yeah. Because I use 0.7. Yeah, actually, I didn't confirm that. Actually, I make these results just denied my hypothesis. If we only use bootstrapping without control of the the depth, it won't work. But um, but as I said before, it should work because I will give you another. I think I know why it doesn't work, but before that, I want you to figure out why it doesn't work. Let's see, as I said before, here, uh, so it's 3 class, right? So if some noise, it should be okay. Some noise it lead to 1. Some noise will lead to 2, but the consistent one always be 0. So that's why, according to Volt, the 0 should appear more frequent than the other 2. But here, why it doesn't work? Statistically, it should work, even though I don't control the depth, because these are random, these are consistent. But why it doesn't work? The reason I think is because of this data set. Um, it's not not because of feature, it's because because it's binary classification. Now I think you get the idea why it doesn't work, because statistically you only have two options, right? So if it has noise, and the noise is it can't be most, it can't lead to other choice. It can only lead to another option another option 0, no one here. So you may can guess. In this case, one will appear more than previously setting, more than the two classes classification. But again, this is my assumption. I still, if you want to figure it out, please verify it by yourself. I also verified it by myself. If in the future I will take the next year machine learning units, I mean student will know, I will discuss that. But hopefully you are interested in this one, why it doesn't work. Just leave another assignment for you, but I will mark it. Okay, so let me go further. This is student tree, okay, all good. But let me go back to this. I don't want ruin this notebook, so I will remove this because I need to continue some content in this notebook. I will go back to this example. I will change back the, the maximum depth is 2. I don't need to change it back. I want to rerun. I want to rerun it and get the result of this from scratch implementation, and also get the result from the sklearn implementation. The reason I want to do that is I want you to be confident that what sklearn does is exactly what I does here. So it will take some time. Okay, nice. Okay, it has a result. Don't look at this result because this result. Oh yeah. I think I have some. What's this random forest? Oh, this is sklearn random forest. But I just the result is doesn't exactly same. You see, here is my result. My result is 78, and this is 50. But here is 88, is 61. Obviously they are not same. But before when I run this code is also not exactly same, but it's very similar. So I must change something here somewhere. Otherwise it should be the same. Okay, I will figure it out later. So after I finish this things, I will go back to this. Okay, so that's the random forest. You can basically rely on the random forest to help you avoid overfitting problem. But as you said, I ruin my code, so you can't say that the results actually become better. It should become better, but let me figure it out. Okay, so now I will go to the bias and variance. I think anyone know if I said I have a variance, I have high variance, does it indicate overfitting or underfitting? Anyone can tell me? Do you have any intuition why the high variance will lead to the overfitting?
It means high variance, actually, again, it's just my understanding, high variance is for the outcome, what we are trying to predict here. So if the variance is quite high, maybe during the training, we went with overfitting. We try to get the right model and get very close for the training. and that's why the outcome is with the high variance. That's my logic on it.
Yeah. Can you specify more on what variance mean here? What variance of what? Because variance is a statistic metric, but here it said variance. It's variance of what?
Variance of the outcome of the prediction or classification as well. It works in both, but I'm just to try to simplify it, make it clear in my mind, because many times they speak about bias and variance in different contexts. So, by the way, in my note as well, I think the optimum to get low variance and ironically low bias.
Yep.
It is quite maybe it's like a dilemma or very difficult to get both of them, because normally low bias it normally give overfitting and give high variance, but I think the optimum or the ideal outcome to get low variance with low bias, which we did will train, but it's not too much close to the data, and then we get low variance and hopefully low bias as well.
Yeah. Okay. Let me summarize what Amar said.
Variance, for here in this context, the variance means we were not able to generalize the model. Like for particular training set, we train the model, and if for different training set that model will not work because it is because we are too close to previous training set. So variance means we have not figured out the general formula of the data set, any relationship.
Yep. All both answers are correct, and that's good answers. And I just want to go a little bit, formulate. But I think that's understanding. Let me summarize it. I think that's. I just want to. Firstly, Amma said the high variance means overfitting, correct? And secondly, Amma said the variance means variance of prediction. That's also very good, because not many people really think about what's the variance about. And most specifically, it's about the test prediction, right? Obviously, it's test prediction. And but Amma will also talk about the some trade-off between bias and variance, because sometimes we can't get both by low bias and low variance. Sometimes if we have want to have low variance, the bias will increase. That is because normally this variance is because of the complexity of the models. So, but the bias is because the simplicity of models. So if you take step forward, it's because of this. But sometimes you can use the complex models, but you can still get you can still complex model. You can think about it. It may lead to the high variance overfitting, because it has introduced just I hope you have the curve on your mind, just like this. If you have some linear, this is let me go for, this is a linear relationship in the training data. So you only need a linear model to do the prediction. But if you have have a polynomial, so models, you maybe can have this curve. You see, it's just completely overfit the training data, rather than to give you a very general linear capture general linear relationship. So that's problem. But still, sometimes you can introduce some, some regularization techniques. I love complex function, but I want to make some, some regularization on that. Now I introduced regularization. As a previous example, you use L2, L1, L2. That's one thing. For this polynomial function, you can maybe, how many curve you have is because this exponent here, right? So if you said, okay, could you make it, you want to make regularization on this number, you want to make this exponent, you also want to minimize this exponent to combine it with the maximum likelihood estimation objective. Then in that case, you have complex model. That's good. It will then you have maximum likelihood estimation. Basically, maximum likelihood estimation is said, okay, just go for my training data. If my training data do well, that's okay, right? But now I add this regularization. I said, I don't only want the training data become perfect. I also want the p become small. So in that case, I have a less complex. The polynomial function itself is have some complexity, but if you introduce this a regularization, it will reduce the complexity of your model. So now you have the model will automatically learn not only your not only your training data, is also have some prior of what kind of function it prefer. I think that's a good. That's why regularization can help you to. I can't say always because it's obviously not always, but sometimes it will help you achieve bias and variance trade-off. Yeah, that's the case. Besides, if you want to go deeper into these things, I think there are a lot of content for this. So you have to look at. I'm not sure which material you need to look, but I think the practice is the best way to learn this, because from my experience, these things are very tricky. So you have a lot of nuances. You only can figure it out doing the practice. So actually, I want to teach you more, but actually I can't because I don't have too much experience to tune this. So yeah, so Amma gave you these 3 points. Okay, so it's very it's very useful. Okay, so just remember this. But the last point I have to mention is I want to make it formal, make it mathematically formalized. So you can, why I want to do that? Firstly, it will enhance your memory, because secondly, it will connect, definition to your mathematical skill. So, yeah, I will do that. But before I do that, I want to ask people, all of you, if I want to, okay, let me introduce that. Then I will ask this question, because then this question will be more specific. Okay, let me formally do this. Amma says it's about the prediction. The second point Amma raised, right? It's about the prediction of test data. But let me have, yep. It's about the expectation of the test, error of test data. What's the expectation? Expectation is just average. So, but my question is average of the each one prediction. You know what I mean? Here we have for each example, we have test example 1, we have a many prediction from this one test example. But after you train the model, you only have one prediction because the model is fixed. The one fixed model only gives you one prediction. So in this case, if you want to have a metric to tell you whether your model have this variance of bias, how you can do that? Any idea for that? How you can produce many predictions? But of course, one model can only have one prediction. So you need more models. So how you can generate more models? I expect some answer. I give you 3 minutes to think about this question. But before that, any question for my question? Any question for my question? That's interesting. It's variance of prediction. You take prediction as a random variable. Now you need to sample a lot of, samples, lot of examples from these random variables. Run more test set. We only have one, we only have, oh, yeah. How could we, we have one fixed test set. How we can run more test sets? Actually, that's interesting because in this case, Margaret said, okay, previously my question is, okay, for one example, for one specific text example, how could you generate different prediction? But Margaret said, okay, forgot that. How about I fix a model, I just generate more test sets. Then I have a prediction on first test set, prediction on the second test set. Yeah, run with different samples from the same test set. I think, Margaret, you mean you do some sampling technique, like, like bootstrapping do something like that, right? Of you just using other sampling techniques. Yep. So then you can do the work. Yep. That makes sense once you only see one perspective of this question. That's also the mistake I made at when I learned these bias and variance things. I do the same thing as you do. I just run more test set. I fix the models, so I have more prediction. Then I evaluate the variance of on these test sets. Then I find, okay, it does not give me the correct result. The model actually has high variance because I'm using decision tree, but it doesn't give me the good result. So I made a mistake here. So what mistake I made here? Go back to look at this. The mistake I made is that I actually don't distinguish this mathematical formula and this mathematical formula. What we do, Margaret, actually is for this. We fix the train and X train. Then we calculate the expectation of the errors on test set. But actually what bias and variance care about is this. This is called marginal expectation. Why is marginal? Because it's just don't have this condition. It doesn't fix the training data. So that means you have to consider different training data. That is inherent property of the bias and variance. That's also what's the difference between bias and variance and overfitting and underfitting. Because people always say, okay, but that's correct. As Amma says, high variance means overfittings, indicate overfitting, but they are not the same. Variance care about the general algorithm. this algorithm can be trained on different training data. It's care about the algorithm on this task. Task is fixed, but training data can be different. That's the key idea. So yeah, so in this case, what should we do? I need to change the different training data. I need to use different training data to approximate this for bias and variance. What should we do? As your answer is very great, Margaret. Actually, that is also my answer long time ago. It's really a trick. Can you repeat the question? Yeah. My question is actually now my question should be very concrete. My question is how you can have a different training data and different test data to generate different errors. Then we can calculate this because this is where the bias and variance come from. Let me just do one step further. Why I said this is where the bias and variance come from, because formally how we can derive bias and variance, this is errors. Actually, your errors can be derived in this form. This is actually the bias. This is actually the variance. This is a prediction. This is the average of the prediction. So for each text example, you have a multiple prediction. This is a mathematical formula. But just go one step back. My question is how if you want to calculate this of bias and variance formula, you need multiple training data and multiple test data. You need to train different models under different training data and calculate the different prediction for each test example. Great, Amma. That's the answer for this question. That's what normally people will do to say whether their model has bias and variance. I think you also give me the correct results. So now you have the answer. Why I bring it out? Why it is practical? Because in week 6 and week 8, I think you come across these things. You see, your test accuracy is 100%, and then your training accuracy actually is also high, but it's not perfect as test accuracy. So in this case, model has looked at this training accuracy, but it doesn't look at the test accuracy. So normally the training accuracy should be higher than test accuracy. So in this case, is that enough? Is that okay? My test accuracy, so my test data is not reliable. So actually, my test data actually is easy. So that's why I get so much high accuracy. So I can't do anymore. I can't do more analysis. No, you can't, because is this doing 100% test accuracy due to the easy examples from splitting? You can test that, because another question should be of because the ML algorithm face this task, right? So which one it is? Now you can use bias and variance. You need to care about different training data, different test data. So you use you use the cross validation. You have different training data. You have different test data. So you do the cross validation here. You do cross score. Then I have which model I have? Logistic regression of decision tree. Why it takes me so long? Let me I just run this one example. So okay, it's good, right? 100%. So now I use cross validation. So it will give me, 4 predictions, right? Because it's, I think how many fold I have? It depends on how many fold I defined. I want to define 5 folds, so it will give me the 5 test predictions. So now you have different predictions. Now you can calculate the variance, right? Now you have predictions. Now you can calculate the variance. What's the variance? NP val, right? That's the variance. Actually, now you don't need to. Actually, this is very easy to look at because it's only 5 folds, so you can have a look. Okay, it's not much different. All of them are very high, so you will say, okay, no problems. I will answer it. My answer is because ML algorithm fits this task rather than only because some easy example. So I can do such such conclusion. But normally, if you have a lot of data, you have a lot of folds, so you want to make your approximation accurate, so you will have a different prediction. You can directly look at the variance. So if you run this, you see, oh, the variance is small. So actually, my data is real. My machine learning algorithm really fits this task rather than the test data is not reliable, is easy, something like this. Okay, so any question for this? Okay, that's so good because this is the most abstract content in the whole machine learning unit. So if you understand this, it's really awesome. So, and I also do some other I actually do some other uncommon work. This work is not actually I don't see any people do this, but this is what I want to have a look. What I do is, okay, here once you do the cross validation, actually you change your test data, right? The test data is not fixed, so every accuracy you have here, this calculate on one first fold, this calculate on second fold, and third fold, fourth fold, fifth fold, right? But this according to this, I think the test data should be fixed. So what I do is, okay, I want to do the cross validation to train different models, but I don't care about the accuracy on the validation fold. What I care about is I have the different models. If I have different models, then I can do the prediction for each one, for each example, for each test example. So my test data is fit. It's not okay. Now I test on first fold. Now I test on second fold. All the tests is on the test data. I only have one test data. So now I have a 30 fold. So I have 30 examples, 30 prediction for each test example. Then I calculate the variance. I think that is also another case you can calculate variance. Actually, I tried this on the overfit data I showed you before, the highly correlated data using decision tree and random forest. And for the decision tree, I get the result of 0.109. So, and for random forest, I get 0.0421. So actually, you can see the random forest actually gets less variance compared to the decision tree. That's what we want, right? That's why we need forest. Okay, so that's all the stuff for today. Any question for this? All good. I think one takeaway you can get is before go to this workshop, you may know high variance mean overfitting and something like this, but now you will know if you overfitting and underfitting is specific for model. of course, you can generalize this idea to algorithm, but bias and variance are talking about the algorithm itself, whether the algorithm fit to the task, rather than specific model trained on specific training data. So this is takeaway.